Okay, Math 170, let's try this one more time. We're going to look at the 5.2 last example in the section. Little different than what we've been dealing with in the last 6 examples. I want you to notice that when you read this problem, yes, it says find the volume of the solid whose base is the region bounded by the curve 4x squared plus 9y squared equals 36, and whose cross sections perpendicular to the x-axis are squares with one side on the base of the solid. Let's notice, for one thing, the words rotated, the word revolve, that is missing. So whenever you're not rotating anything around axes, we will not be using discs, our washers, or shells. Eventually you'll see what I'm talking about. So what you want to do in this type of problem, we're going to try to consider it. It's kind of like, in a sense, a loaf of bread. And the base, instead of being a nice clean cut geometric shape like square, triangle, circle, the base is actually varying based on the curve given. So that's our 4x squared plus 9y squared equals 36. The other thing we'll pay attention to is when they talk about the cross sections, I'll be clear on that. The cross sections are perpendicular to the x-axis. So that's giving us a heads up that our thickness is always going to be defined as our delta x. The other idea is understanding what does it mean when the cross sections are perpendicular to this x-axis, or the cross sections are perpendicular to the base. And so you got to picture this like a slice of bread. So that's the best way I can describe it. They're considered to be squares. So right now I have the graph of the equation. It's an ellipse centered at 0, 0. And then we have vertices and co-vertices so that we have an accurate picture. But when we draw our particular square, I want to show that it's situated in the sense, it's somewhere along this line. We know that the base, if we were to imagine it coming out at us, the base can be designated by the points located along the ellipse. So we have a point x comma y, and by symmetry, we notice that they have the same x values and opposite y values. So what we can look at is when I'm trying to understand what is this supposed to be, when they mention square, you have to picture this square coming out at you, 3D. So you're facing above and we're facing below. So what we need to see, I think I have this great applet. I hope it'll load this time. Yes. Right here, we have a 3D representation of what is actually going on. So if I can take my base and move it along, you kind of notice as I move my square, or as I look at the particular cross section, notice how the square is getting smaller or larger depending on its location along the ellipse. Do that one more time just in case. Notice when you get to the vertices, it gets really small. So you have a bunch of squares. Now, also having said that, if we're trying to understand how this works, eventually we're going to have a bunch of squares so that we slice the solid up so fine. If I can do this, we have more squares going along. So if I can kind of show you, as I'm moving along, you see that what shape square it takes as we go through the particular solid. One more time. So pretty, huh? And the idea is to make more squares and slice this solid up so thin that it ends up taking on the shape of your geometric solid. So we have a lot of squares, and you can kind of see that the size of the square changes along the way. I mean, the area of the square changes along the way. So you can see different versions. I'm only going to do one example with you, but different versions and different shapes, depending on who the base is. You could have rectangles as your particular base. I'll kind of go this way for a second. So you can kind of see that it does look similar to the square, but as you go along, the shape of the rectangle changes, or the width, the dimensions will change, base and height. So that when you see the solids, as you slice it up, you'll see that the more rectangles you make, the different shape it makes. So you kind of see from there. It's really pretty. Okay, and I also want to show you, we do have like equilateral triangles. That's also an interesting one as well. You can see as you move along the ellipse, the 2 points, the base gets wider or smaller, and that kind of also has to do with what's happening to the height. So then if you want to attach on some of your triangles, you can see the shape that it makes. And now you could also see that it's slightly different than what we saw with the squares. The more squares we have, and you can see as we move along, the size of the triangle is going to change. The area of the triangle is going to change. One more, just in case we want to visualize this. We can do this with a circle. I'll do this with a semicircle first. See if I can find it. And we can kind of show that, oh yeah, it's moving along. And if it's a semicircle that's coming out as a cross section, when you add more of them, again, you see how you are getting, this one looks like more like a half a watermelon than all the other ones. And it's green. So you can see as you're moving along. So that is the idea. So you can kind of take this and adjust it based on what you have. I do have this located in Canvas. But we were based on squares, just so that we all see. And our idea was that we were making up a bunch of squares to get the actual volume of this solid. So the idea, first off, is to understand how do you calculate volumes in the first place? And the other idea is, how about we find the area of one of these squares? So let's go back. And go back to the idea, if we are finding the volume of one cross section, we basically are dealing with a formula, area times thickness. Just like we did, in a sense, when we were dealing with the previous examples. Now, we already know the thickness based on being perpendicular to the x-axis. We already know that we're going to have the cross sections will have a delta x of a thickness. But now we just have to understand what item we are trying to find the area of. And you could kind of say, like, okay, it's got to be that square. So we know in sense of areas of squares, if we're trying to label the sides, it's side times side. But if we want to, we can kind of attach this to our formula. So the area of the square times the thickness. If you want to attach this to the orientation, it is in terms of the XY coordinate system, we're going to need to understand what's the length of the side in terms of X or Y. And the way I see it in terms of the points, we're looking at it slightly different, but we're looking at going from negative Y to positive Y. So what happens if you're on the coordinate system, you have a distance of Y and Y. So that makes that length of the side Y. So now we can replace this, and I'll take out the coordinate situation so that we can see. We can replace this S with 2 times Y. So now we have the 2y squared. So that's kind of where I'm developing this. If you want to see this one more time, just so that we can understand what was our purpose, let's go back to our cross section. And you could clearly see, okay, yeah, it's a square. And again, the y values change based on the location of where the square is, the length of the base or the side. So it's good to kind of recognize. So we can go back and let's look at our calculations. So we've got S is now going to be rewritten as 2y squared, and we're still multiplying it by delta x. That's our thickness. So we have 2y squared times 2y squared is 4y squared. And we still have it multiplied by delta x. Now, remember, when you're finding this, before we even start talking about integration, our variable portion must agree with the variable we are taking the integral with respect to. So our 4y squared, we actually have to agree with delta x. So we have to come up with a relationship between y's and the x's. And that is actually found by the curve that's given to us. So that's the 4x squared plus 9y squared equals 36. So when we do that, 4x squared plus 9y squared equals 36. It seems more appropriate just based on the formation of what we have in our volume calculation. If we solve it for y squared, we're going to be in good shape. So I am going to solve this for y squared. So that will leave us with 9y squared equals 36 minus 4x squared. And if we divide everything by 9, I'm going to get y squared. Might as well do this manually so you can see. It makes it a little nicer if we don't have a huge fraction. So we have 36 over 9 is 4, and 4x squared over 9 is still 4x squared over 9. So now we can replace that y squared. Take that y squared, replace it with 4 minus 4x squared over 9. We still had this 4 multiplied by the y squared. We still had this delta x. And now what do we always tell you? Before you even try to integrate, clean it up. So we should have, there's a couple ways to go. I can distribute the 4 and say 16 minus 16x squared over 9. Still all multiplied by delta x. And if you're inclined to, you want to maybe factor out constants and make it a little prettier with no fractions. This is just us getting fancy, totally up to you. I do know for sure a 16 factors out. And if I want to also maybe get rid of the fraction, if I take a 16 out of 9 out, or 16 ninths out, we should get, if we're kind of trying to understand what the inside is, 9 minus x squared on the inside times delta x. You don't have to get fancy. It's just kind of sometimes having that constant out of the mix helps, but totally okay. So now, finally, we get to talk about the volume of the entire solid. And it's similar to how you think. Think about where you're moving towards. If we're taking everything with respect to x, remember everything's delta x dx. Thinking about how we're slicing up our x-axis. We're slicing up our x-axis. So that means we would take our vertices as our limits of integration. So we should be looking at -3 to +3. And then we can replace our 16 ninths. I'll color code that. 16 ninths times 9 minus x squared. And that's cool. But you could also notice, either way, if you use symmetry, you could look at the fact that the ellipse is centered on the origin. So if you want to take a portion of the ellipse, a fraction, and in fact, it looks like it's exactly a half, we can change our limits of integration from 0 to 3. And that might be a lot quicker to evaluate. Let's say if you're trying to do this by hand. So if you were, you could say, well, that's 2 of those, because we're talking about halves, 2 halves of an ellipse. So we would take the limits of integration from 0 to 3, still have that 16/9 times 9 minus x squared with respect to x. So either way is going to work. If we're using a TI, it won't even matter whatsoever. So feel free, have fun. If I'm using a TI, I'm not concerned about limits of integration. I don't have to worry too much. But I can take the 16 out of 9 out of the situation. I can plug in everything to my TI. And my TI should give me, with that, it actually gives me 36. So notice there's no pi involved because there was no revolution, disk, or washer. We were talking about shapes. So what then goes on, we finish this problem off by multiplying it by 16/9. And if you want to use your calculator, you should have 64, but what do we need? The units. So it'd be cubic units because it asks us to find the volume. So this would be how you approach this type of problem. Again, keep in mind, the way we're looking at things is we never rotated or revolved anything. Everything's based on stationary base of your curve. And your two-dimensional figures are coming outwards towards your curve. So that's what they always talk about. Cross sections are perpendicular to the XY plane. So hope this helps you out for that last part of the section. We will see you in section 5.3.